So let's rush to the this presentation session, which is having got a very burning topic of acquiring 20-year furnace campaign. That is basically our agenda point, and our discussion of the presentation is in only this direction. So looking at the title graphic, you see a step transitioning from a stable mm, to a catastrophic molten orange. So this is a reality of modern high productivity operations. So today I am going to provide you with the three critical deliverables. First, a root cause analysis of why rolled copper strips are failing prematurely. Number one. So, and what is the second? Second point is the specific thermal threshold that trigger irreversible metallurgical decay. And finally, a blueprint for a multi-sensor fusion architecture that guarantee a 20-year campaign. So we are not just looking for incremental improvement, we are looking to transform the furnace from a volatile thermal mystery into a deterministic high yield asset. So understanding this transition from stability to failure is paramount, which leads us to directly into data behind the current longevity gap. So to solve the failure, we must first quantify the delta between our engineering expectations and the harsh operational reality shown on the next slide. So, friends, we have a crisis in our capital baseline. On the left of your screen, the metric table highlight a sobering reality. While we engineered for 15 to 20 years, we are seeing actual campaign lives for only 6 to 8 years, 5 to 6 years rather, in high pallet burden environment. So notice the central 3D visualization. Uh, the timeline axis shows a stable blue path for the first few years, but then we hit a capital destruction event where performance drop off a cliff. So the data shows that hit load exceeding 4 lakh watts per square meter, double our design expectation of round 2 around 2 lakhs. When your hardware error is unknown or blind, you are essentially operating in the dark. These sudden premature performance drop is not just a maintenance headache, it's a massive destruction of value that affect our total plant cost and rather smelting kinetics. So to stop this bleeding, we need to map the specific degradation path that leads to this failure. And this catastrophic drop is not a random. It follows a predictable sequence of event. We call that PSPP path. So coming to our next slide, which is talked about this uh, PSPP path, degradation path. So to manage a system, you must understand its failure mode. And this slide break down PSPP, that is P stand for process, S for structure, P for property, and performance degradation. So this is all about. So follow the flow from left to right. It begins with the process where the edge airflow matters, then which is highlighted in the cyan. Strip away our protective slag. So without that slag, we move to a structure where the loss of the slag crust exposes the copper to extreme thermal spike. So this trigger the property phase, that is a hydrogen embrittlement. And look at the orange glowing stave segment. That color represent the internal stress leading to the final performance stage, a complete stave rupture, shown in the vibrant red. So note the normalized damage signal on the right. Once you hit the slack crust loss, your damage signal jumps from zero point 0.2 to zero point 0.5. So this progression is the silent killer of your heart. So if you want to intercept this failure, we have to look closer at the chemical tapping point known as the hydrogen cliff. The most dangerous point in this sequence occurs when the copper reaches a specific lethal temperature. And the and our next slide, which is showing about the hydrogen cliff. This is the most important chart you will see today. We are looking at the hydrogen cliff where performance integrity is plotted against the temperatures. Notice the stable CN line up to about 200 degrees Celsius. We are in a safe 10-year plus zone. But follow that line to the 370-degree mark. It doesn't just dip, it plummets. In a reducing atmosphere, penetrating hydrogen react with stress oxygen instantly, tearing the copper matrix apart from the inside. The ACM micrograph in the center shows that the grain boundary tearing, those bright orange fissures, are the physical manifestation of hydrogen embrittlement. So look at the time to cracking data at 370 degrees. You have less than 70 hours until your total failure. This is not a slow wear process. It is an instantaneous metallurgical death sentence that destroy our cooling capacity and risk a breakout. So this brings us a fundamental paradox in how we select our material. We often choose the purest material for the conductivity, but that purity creates its own set of mechanical vulnerabilities. So coming to the paradox in our pursuit of thermal conductivity, we have created a purity and wear. Uh, mm, so we use ultra pure rolled copper shown in the left half of the central split screen. Uh, as you can see, so it boasts a conductivity of 315 watt per meter Kelvin. However, as the blue tinted image shows, this material is fatality shaft. Without upward ribs, it sheds its protective slag crust and functions like glass under abrasive edge airflow. Now look at the right side of the image in a alarming pink, that is catastrophic mechanical wear. The table compares material grades. While rolled copper is more than 99.9% pure, its slag accretion is rated as poor. Conversely, cast uh, in steel copper, though slightly lower in pure conductivity, provides excellent slag retention. This means that by chasing the highest possible purity, we are actually inviting faster erosion because the material cannot hold a protective layer. This a lack of protection create a massive diagnostic blind spot in our monitoring system. So if our material are failing, we need to know exactly when and where. But our traditional sensors are lying to us. So traditional monitoring is failing us because it rely on the thermal and acoustic signals uh, that drift as refractory layers which degrade. So on the right you see a cross section of the hearth with a EMF vector arrow cutting through a hot metal. So traditional thermocouples as noted in the table suffer from high drift, meaning the data you see today is not the same as the data from the last year. Acoustic reflections like UT have moderate noise due to complex internal geometry. Electromotive force or the EMF sensor provide a thermoelectric signal with a precise error rate of only 6.8% to 10.3%. By measuring the actual millivolt generated by the thermal gradient, we get a real-time diagnostic clarity that the thermocouple simply cannot match. This allows us to move away from the guessing the thickness of our remaining refractory and towards a deterministic model of the furnace health. So this clarity is what allows us to define our operational phase map. With accurate EMF data, we can finally define no-go zones for our furnace operators. So coming to our next slide, which is depend on uh, the operational phase map. Uh, so survival in the modern iron making requires absolute discipline. There is no doubt about it. This operational phase map defines our zero tolerance parameters. The graph shows that heat load over time divided into three distinct zones: safe, warning, danger. Safe, warning, danger. The safe zone is the green area where hot phase temperature remains below 180 degrees Celsius. Once you cross that first cyan um, threshold, you enter the warning zone. But look at the red picks on the right. That is your danger zone. If your hot phase temperature exceeds 370 degree, your peak heat load tops 4 lakh watts per square meter, or your cooling velocity drop below 8 tons per hour. So you are inviting irreversible metallurgical decay. So you can see that danger phase detected alert at the top right at this point. The damage is done. To stay in the green, we need more than just better software. We need a mechanical upgrade to the stave itself. So we must move from deforming soft copper to a rigid engineered solution that can handle these loads. So coming to the mechanical upgrade, and so here is the solution to the mechanical failures we have discussed. The cast in steel upgrade just a few time back. On the left you see a standard rolled copper strip in pink. It is deforming under weld stress and has shallow reefs that cannot hold slack. Now look at the cyan, that is cast in steel pipe, that is copper strip on the right. By casting copper directly around steel pipes, we eliminate internal thermal weld tearing. Notice the perfect integration call out in the circular inset. The copper and the steel are unified. Furthermore, those massive upward facing ribs mechanically lock the slack crust in the place, shielding the copper permanently. The table below confirms deformation risk is negligible because the steel pipe handles the expansion, and slag retention is excellent due to the rib geometry. This is how we move from a soft consumable to a rigid permanent component. But even with a better hardware, we still need intelligence to predict the future. And mechanical rigidity is only half the battle. The other half is the predictive intelligence. So coming to our about the intelligence upgrade, and where we are ending the era of reactive firefighting. This slide displays the intelligence upgrade using predictive EMF. The central graph shows the real-time EMF levels. Notice the blue present day line. To the left we see the historical data. To the right in the orange we see the highly accurate prediction curve. By embedding EMF probes deep into the graphic brick, we generate a wear forecast decades before a breakout could occur. So look at the target zone level 8494. The current thickness is 1200 mm and our EMF prediction here is about mere 0.3 mm per year. This gives us a time to critical of over 20 years. We are not just reacting to today's heat. We are managing the thickness of the hearth wall for the next 2 decades. This fusion of rigid hardware and predictive software creates what we call that 20-year architecture. So let's look at how this entire system comes together to deliver a massive return on investment. So the 20-year architecture about which our slides is all about. So we have covered a lot of technical ground. So let's look at the bottom line. The 3D wireframe on the right represent our total metallurgical health model where the predictive monitoring is active and the asset state is stable. So look at the executive ROI summary table, the status quo Using rolled copper and traditional thermocouples lead to high maintenance and a 5 to 6 year life. By implementing cast in plus EMF, we see a plus 12% upfront capex impact. However, that 12% investment buys you a 20 plus year campaign, a 4 time life multiplier. So we are transforming the blast furnace from a volatile, high risk system into a deterministic, high yield asset. Reactive firefighting ends today by combining the mechanical strength of cast in steel with the diagnostic clarity of EMF. We can finally guarantee the 20-year campaign our industry demands.